So, welcome in this lecture, and this lecture is based on non-orthogonal coordinate system and how idea of covariant and contravariant factors will be evolved. In the earlier lecture, I talk about orthogonal coordinate system, and it's like a projection. So, as I talked earlier, that vector can be expressed in the form of a projection along different axes. Projection along different axes, and projection is nothing but it is the shadow. So for example, I am having a vector say this is a vector and this is axis, say it is a ground. So if I am having a source of light above it, means it's parallel to x-axis, then it casts shadow, means if light is coming parallel to it, so then these are the parallel beams of lights which are coming. In this form, then this is the shadow region. The shadow region. This is the shadow region. This is the shadow region. Right? And if light is coming from this direction, say it is x-axis, means here the source of light is perpendicular to x-axis, and if source of light is parallel to, say it's a source of light, it's a parallel to this y-axis, means here the rays are coming in this way, and if source is here and it send rays in this direction, then in that way, so light is coming in this direction, this way. So if things are happening in this manner, then this is the shadow region. This is the shadow region. And if this is vector A, then this distance, this shadowed portion, this is known as AX, and this is known as AY, and this A is known as AX EX plus AY EY, and these are the unit vectors. So that's what will happen. That means the vector is expressed in terms of a projection along different axes. And it's not necessary that source of light is always perpendicular to different axes. Especially the case when these axes are not perpendicular, then what will happen? Then different cases may arise. Let us consider another case. If some object is somewhere here, then different possibilities are there. Say, if source of light will be somewhere here, this is source of light, and light is coming from here in this way. This is coming in this way, light is coming in this manner. To say that light is coming from this direction, parallel beam is coming in this manner, and in that case, this is the shadow region. 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 So this is the projection of this vector along this direction. But if the source of light will be somewhere here, then what was the projection? The projection is in this direction. So let us have a look at the projection. So light is coming in this way. It's a parallel beam. And this was the shadow region. This is the shadow. This is the projection. So that means this is equivalent to this shadow. It is equivalent to non-orthogonal coordinate system, and this corresponds to orthogonal system. And now we will use this idea of projection is used to develop a new mathematics where x-axis and y-axis are not perpendicular. That's the purpose. And the axes which are not perpendicular, such type of mathematics is useful in relativity and fluid dynamics and in other fields also. So let us consider the case when axes are not perpendicular. See, this is x-axis and this is y-axis. And say there is some vector A somewhere in this. Let me call it as x-axis, it is y-axis, it is x-axis, and it is y-axis. So there are different cases, different possibilities. Say the source of light is sitting somewhere here. It's a perpendicular to x-axis. Similarly, I am considering a source of light which is somewhere here. It's a perpendicular to y-axis. That's perpendicular to y-axis. So now what will happen? If it is perpendicular to y-axis, means light rays are coming perpendicular to y-axis. So rays are coming perpendicular to y-axis from here, and here the rays are coming perpendicular to x-axis. So if it is happening, then say rays are coming in this way. So now the rays are coming in this manner. This is the direction of rays coming from the source in this direction. And similarly, in this case, the rays are coming in this way. So light is coming in this way. So that means the projection of this vector is this one. This is the projection of this vector. This is the shadow region for this vector A, and for this vector this is the shadow region. So this is the projection of this along this way. So this is the shadow cast by A on x-axis, and this is the shadow cast by A on y-axis. So these are the different possibilities. So for this, let us take two different cases. This is the general idea. Now be more specific by considering two special cases. Say this is x-axis and this is y-axis. This is y-axis, this is x-axis. This is x-axis and this is y-axis. And say there is a vector A. It is somewhere here. It is vector A. Now I will consider the cases when rays are coming parallel to axis. Rays are parallel to axis, and here the case when rays are parallel to, here the rays are parallel to axis, and here the rays are perpendicular to axis. So for this, let us do one thing. Its rays are coming parallel to axis. So that means the source is somewhere here. The source is somewhere here, right? And source will be somewhere here. So, let me take another color. Say this blue line represents the extended source of light. As I said, this is the extended source. This blue colored represents the extended source of light. Similarly, I will draw the extended source of light somewhere here. Sorry, it's a perpendicular. It's now perpendicular, right? So let me consider extended source will be here. It's a perpendicular to x-axis. So that means I will draw extended source here, and here the extended source will be this one. So this is the extended source. This is the extended source. An extended source of light represented by this blue colored line. And now this will throw radiation, or this will throw light in this way. So it will throw radiation or the light, say, parallel to y-axis. So this is a parallel, this is parallel to axis. It's a very interesting case. right? So that means these are the light rays coming from this extended source in this direction. And this extended source, which is located here, it will throw rays in this direction. That means if this is parallel to this one, right? So from this extended source, light rays are coming in this way. Right, so light rays are coming in this way from this extended source of light, means parallel to x-axis. So yeah, this is the direction. So if this is happening, then what's going on? So that means this this is the shadow region. This is a shadow region which I am getting from this source of light. And also, if light rays are coming in this way, then this is the shadow region. This is the shadow region. This is represented, say, with the blue color. This is the shadow region. That means the projection of this is the projection vector here, and here this is the projection vector. So let me call this as AX, and let me call it as AY. But for the sake of simplicity, let us replace this AX and AY to just make a difference AX and AY, as it is a non-orthogonal. So that's why let me call it as AY, and it is AX as a subscript. I am writing it as. So if I try to look at it, then what's going on? That now this will become a parallelogram. This will become a parallelogram. So that means if I apply the parallelogram's law of vector addition, then this vector A can be expressed as a sum of these two vectors. Or in other words, I can say that A vector can be written as AX, not AX, but AX vector plus AY vector. We will talk about this in later on. So that means in parallel projection, when the light is coming parallel to axis, then that means components formed by parallel projection add to give the vector. Right? This is the one conclusion which we are getting. Because it will become a parallelogram, so that means this vector is simply written as the sum of these two vectors. This is simply a parallelogram law of vector addition. But let us take another case. In another case, light is coming parallel to axis, and if light is coming perpendicular to axis, then what will happen? That's a very interesting case. So let me draw a diagram. Here the light is coming from this extended source parallel to axis in this way. perpendicular to x-axis. The light is coming perpendicular to x-axis. And from here again the light is coming perpendicular to axis in this way. The light is coming in this way from this extended source. If things are happening in this way, then this is the shadow region. 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 And also for this is the shadow region. This is the shadow region which I am getting. This is the shadow region. This is the one region, this is another region. And here the vector formed will be this one, and another vector will be formed this one. And here the vector which I have chosen, that vector is this one, right? So this is a vector A, and let me call it as y vector just for the sake of simplicity, and let me call this as x vector. Now this A vector can never be written as x vector plus y vector, because no parallelogram will be formed. Means no vector addition law is valid. But this diagram will suggest something. This diagram will suggest something if we try to look at it carefully. If I use these two, because what's going on, that this is one axis, it is perpendicular to this one, and this is perpendicular to this. If I use these two, and if I try to look at their projection, if it is in this way and this is in this way, then it will become a parallelogram. That means if I choose these two as basis directions, as a basis, if I choose these two directions, then this will become a parallelogram. Otherwise it will not become a parallelogram. That means if I make use of this thing, then that might be help us. So that means from this portion, this region, what we are concluding, that components, this is a very interesting conclusion, that components, which components x and y formed by perpendicular projection do not add to give vector A. That's what we are concluding from the perpendicular this. So to make the idea of, first we will consider the case of parallel projection parallel. Rays are parallel to axis and rays are perpendicular to axis. Here we will get the same vectors, and for the sake of simplicity, let us assume it as AXE1 E1 vector plus AY E2 . This is valid for this case, but this is not valid for this, as I talked about earlier. And here, what is E1 and E2? These are the basis vectors. These are the basis vectors. Let me recall earlier diagram. In this direction, or let me draw another diagram. That will be much better. So, for this case, let us consider a diagram. Light ray is coming in this way. There is vector sitting in this manner. There is a vector. So, if rays are coming parallel to this axis, rays are coming parallel to this axis, and here the rays are coming parallel to this axis. So that means this is the shadow region which I am getting. This is the shadow region. This is the shadow region, and here this is the this is not the shadow region, but for this, because it is coming parallel to y-axis, this is the shadow region. This is the shadow region, and here this is the shadow region. And let me recall that this is the, along this direction, let me call it as this basis as E2 vector, and along this direction let me call it as E1 basis vector, and say if it is in this way, then this distance is nothing but means the distance which I have taken from this point to AX. It is from here to here. It is a shadowed region from here. Yeah. So let me call it as it is AX, and similarly this distance which I have chosen, let me call it as AY. So that means this vector is AXE1 vector. It's along this way, and this vector is represented by AY and E2 vector. So that means this is simply the sum of these two vectors, because it forms a parallelogram. Right? So this is according to parallelogram law of vector addition. And here, another very interesting thing, that I have chosen AX and AY for a parallel projection. And this parallel projection is also known as contravariant. It's known as contravariant. These are the new terms which we are getting. Contravariant for the parallel projection we are using as components of A. This is just to make a difference from the contravariant formalism, where we will use the perpendicular projections, right? And these are the standard notations. Need not to worry about that why we are taking. They are simple notations which we are taking. Now, if we try to look at the perpendicular projection or recall the idea of the perpendicular projection, then they do not give us the same vector. That was the problem, right? So if that was the problem, then how to tackle that problem? Let us consider two diagrams again. So let us make a line here, and let me talk about perpendicular projection here. So for the perpendicular projection, say these are the vectors, and say it is the x-axis. That means we need a equation, new equation, which is analogous to this equation 1 for the perpendicular projection. But there is some problem with it. So what do we do to do that? This is one, and this is another case. And say this is a vector which I'm trying, right? So light is coming perpendicular. So if light is coming perpendicular, that means first of all, where I will draw the light is perpendicular to x-axis. So if light is coming perpendicular to x-axis, then it looks like this. The light rays are coming in this way. And here light rays are coming this way. So here this is extended source and light rays are coming perpendicular to this. In this way. So things are happening in this manner. Now, as I see earlier diagram, so if I compare with this, then this is basically, this direction is E1 vector. This direction is E1 vector, and similarly here this direction is A2 vector. As I compare with this, and it is E2. And this is vector A. This one is the vector A. This direction is E1. So its projection will be, if we talk about the projection of this vector along this is the projection direction. This is the projection of this. So that means if we talk about it, then its projection will be along this direction, will be this one. This is the projection region. And here, this is the shadow region. This is the projection of this direction. but these two vectors will not constitute, means their sum will not constitute the vector A. This is the problem. So for this, what I will do, I will make arrangement, a new arrangement. And what is that arrangement? I will draw one vector here perpendicular to this y, this vector, this y-axis. If I draw a perpendicular to this another vector, say, let me call it as this, right? And say this direction is not E1 underscore, as a subscript, but as a subscript. Let us assume that this is another direction. I am defining another vector or another basis whose direction is this one. And here I will draw another which is perpendicular to this one. It's perpendicular to this one. And say it is E2. So that means I have chosen E1 such that E1 is perpendicular to E2, and another thing that I have chosen E2 such that E2 vector is perpendicular to E1. This is the one condition which they must follow. And if I try to look at it in this manner, this is E2 and this is E1. And let me club this diagram. And if I club this diagram, say this is 1, this is 2, and this is 1, right? And this is our vector. So here, this direction is E1 and this direction is E2, and here this direction I have chosen as, this direction is E1 vector, and this direction I have chosen E2 vector, E2 vector, and my vector is A vector. So it's a perpendicular, so it's perpendicular to this axis. If light rays are coming perpendicular to this axis, then its projection will be this one. And let me call this distance as AX. Let me call this distance as AX. And similarly, if light is coming perpendicular to this axis, as I see here, then its projection will be this one. Let me call it as AY because it's along y-axis, and say it is AX. So its direction is AX. Then this will become a parallelogram. So that means this A vector can be written as AX E1 vector plus AY E2 vector. So this equation resembles with the equation number 1, and that is the idea behind it. So that means now we encounter a new terminology. And what is that terminology? So the basis, that means now we are defining our basis, or you can say that we are talking in terms of new type of or new alternate for the basis vector. So let me recall E1 and E2. These are basically original basis vectors in the parallel projection. Now I will define new basis or alternate basis vector. and we call these as reciprocal or dual vectors. And they have certain characteristics. First characteristics is that each alternate vectors are represented by E1 and E2, and 1 and 2 are sitting as a subscript, and here original basis vectors, this is sitting as a subscript, and this is as a superscript. This is called as superscript, right? So each one must be perpendicular all original basis vectors with different indices. That means this E1, it must be perpendicular to E2, and E2 must be perpendicular to E1, as I see from here. This is E1 and this is E2, and similarly I have chosen another vector such that it is E1 vector and this is E2 vector, such that they must satisfy this condition. Right. So we have chosen in this way. Another thing, that if they make an angle, say if it is making an angle theta 1 with it, and it will make an angle theta 2 with this, then they satisfy another condition. And what was the another condition or another characteristics of these dual bases? That dot product between each dual basis vector and original basis vectors with same index must be equal to 1. So mathematically, how things can be written? That if E1 and E2 are the original basis vector and E1 and E2, these are the dual basis vector, then the condition they must obey is that this E1 and E1, their dot product always must be equal to unity, and E2, and this is always unity. If this is happening, then we call it as E1 mod. E1 mod, it must be equal to, cos of theta 1, it's equal to 1, or I can say that E1 is equal to 1 over E1 cos of theta 1, and similarly I can write down it as cos of theta 2 is equal to 1. That means this E2 can be written as 1 over E2 cos of theta 2. So that means by defining dual basis E1 and E2, we can express A in terms of covariant components. AX and AY. So to sum up these results, finally, this is A vector. It can either be expressed as AXE1, AYE2. This is the contravariant formulation, and similarly, this is, or you can say that, parallel projection, and similarly it can be written as AXE1 plus AYE2. This is known as contravariant formulation. This is known as covariant, not contra, or perpendicular projection. So this is a new idea which is emerging out from this discussion. So thanks for watching this lecture.